A cable of constant line density is suspended between two vertical poles of equal height such that it takes the shape of a curve y equals 6 hyperbolic cos x divided by 6. The origin of the curve is a point midway between the foot of the poles and y is the height above the ground. If the cable is 600 meters long, show that the distance between the poles is 55 meters to the nearest meter. And we're going to find the height of the center of mass of the cable. So we're given the length of the cable. We're given that it's 600 meters long. We're also given the functional form of the curve of the cable. We want to get the distance between these 2 points. So in previous videos we saw that the length of a curve is given by this formula here, where we're integrating from a to b with respect to x. So here we're integrating from minus d to d. We need to find dy dx for this curve. So here's y, so we differentiate this. Well, the derivative of the of the hyperbolic cos function is hyperbolic sine. And by the chain rule we have 1/6 from the derivative of the argument. So 1/6 by 6 gives us 1 here in front. So we need to plug this in for dy dx and integrate from minus d to d. We have to find d, but at least we know the result is going to be 600. So we have the square root of a quantity. There are 2 terms under the square root sign. That's not good. We normally like 1 term under a square root sign. What we do here is use this identity. Hyp cos squared u minus hyp sine squared u is 1. So 1 plus hyp sine squared u is hyp cos squared u. So we have the square root of hyp cos squared u. That's hyp cos of u. So our integral becomes this much simpler integral. The integral of the hyperbolic cos function is hyperbolic sine. By the chain rule for differentiation we have to put a 6 here, so that when we differentiate this, derivative of hyp sine is hyp cos, and we differentiate the angle to get 1/6, and 1/6 cancels the 6 here. Next we plug in the upper limit, which is plus d, and then we have a minus sign, and then we plug in the lower limit, which is minus d. Hyperbolic sine of a negative quantity is minus hyperbolic sine of d over 6. So this minus sign can come out actually, and we get a plus here, in the same way that the trigonometric sign of a negative angle involves taking the minus sign out. So we get 2 hyperbolic sine d over 6 times 6, that's 12 here. So all we do now is just solve this equation for d. We get d equals 27.63, so we just double this to get the distance between the poles. Next we are going to get the center of mass of this cable. By symmetry, the x-coordinate of the center of mass must be 0, so the x-coordinate has to lie along the y-axis. So here's ultimately where it is, so x bar is 0. To get y bar we will have to consider moments of pieces of this cable about the x-axis. So we will take little elements of this cable. Each element will have length delta s. Here is another such piece, his length delta s. Now the density along the cable is constant. We can let rho be the mass of unit length of the cable. It could be the mass of 1 meter of the cable or 1 centimeter. It doesn't matter. We can make the unit as fine as we like because the density is constant for every point of this cable. So to get the mass of each element, which I will call delta m, we multiply the mass per unit length by the length of an element of the cable. So the length is delta s. So you see, if the units of rho are kilograms per meter and the units of delta s are meters, then you see these cancel out, so we get the correct unit of kilogram for the mass of each element. Okay, we have to get the moment of each mass element about the x-axis, so we want to multiply it by this distance. Well, that's just a y value of the coordinates of each element. So we will be letting delta s go to 0, so the mass element will become a point whose height is y units above the x-axis. So the moment of each element will be its mass delta m times y, which is rho delta s by y, or rho y delta s. Now we want to get the sum of the moments of all of these elements from x equals minus d to x equals plus d. We will take the limit of this sum as delta s goes to 0 now, and our integral becomes the integral from minus d to plus d of rho y times ds, so delta s becomes ds. Now in previous videos we saw the connection between delta s and delta x and delta y by considering this right angle triangle. So delta s is the distance along the cable between these 2 points that are very close together. So delta x is the horizontal distance between them, delta y is the vertical distance. And to a very good approximation, as delta s goes to 0, the straight line distance between these 2 points is equal to the distance along the curve. So the straight line distance between the 2 points is got from Pythagoras' theorem. It's the square root of delta x squared plus delta y squared. And we saw in a previous video that we can write this like this here. We can just divide inside by delta x squared, but then we must multiply outside by the square root of delta x squared, or delta x. And in the limit as delta x goes to 0, this thing here approaches 1 plus dy dx squared, the square root of 1 plus dy dx squared times dx. So we are going to replace ds with this thing after we take the limit. So here is what we get. So we sub in all this for ds. The rho has been taken out, that's just a constant. Now the mass of the cable is the length of the cable 600 by the mass per unit length, which is rho. So we have to calculate this and then divide by 600 rho, the mass of the cable. Okay, we know what y is as a function of x. We know the equation of the curve formed by the cable. So we can get dy dx. We did this before for the previous part, and we saw using an identity that all of this is hyperbolic cos of x over 6. But we have another y here, another hyperbolic cos x over 6. So when you multiply them, we've hyperbolic cos squared of x over 6. Similar to a trigonometric identity for the cos squared function, the hyperbolic cos squared function can be written in a linear form like this. So we get 6 over 2 here, which is 3. We integrate the hyperbolic cos function to get hyperbolic sine, and we need to divide by the coefficient of x, which is 1/3. So 3 divided by 1/3 is 3 times 3 is 9. So that when we use the chain rule to differentiate this, we get 1/3 by 9, giving us back to 3 here. We also have to integrate 3 with respect to x, well that gives us 3x. Now we plug in the upper limit, which is plus d. When we plug in the lower limit, minus d, we have hyperbolic sine of minus d over 3. That's the same as minus hyperbolic sine of plus d over 3. And the two minuses give us a plus when we subtract the two expressions. So we end up getting 9 plus 9 or 18 hyperbolic sine d over 3. So just to be clear again, this is what we get when we plug in the limits. The hyperbolic sine of minus d over 3 is minus hyperbolic sine d over 3. So these two terms combine to give us plus 18 hyperbolic sine d over 3, and then we have plus 3d giving us plus 6d. Now the rows were cancelled from both sides here, so the last step is to divide by 600, but we also have to plug in for d. We found d from the previous part, it's 27.63. So if we solve for y bar, we get 150 meters. So here's the picture. Now the center of mass of the cable is actually above the lowest point of the cable. The lowest point is at 0, and if you plug 0 in here for x, we get 6 hyperbolic cos of 0. The hyperbolic cos of 0 is 1, so we get y equals 6. So the lowest point of the curve is actually only 6 meters above the ground. So obviously this diagram is not drawn to scale. So we see the center of mass is above the lowest point of the cable. Now we know that d is 27.63, so if we plug that in, we can get the height of b above the ground. So we have to get hyperbolic cos of 27.63 divided by 6. And we have to multiply this by 6. Actually, we have to make sure the argument is in radians, not degrees. I had it in degrees. So we want hyperbolic cos of x divided by 6. Well, Well, the coordinates of this point is minus 27.63, but we can put in plus 27.63. Makes no difference for the hyperbolic cos function. Get a positive answer. So we have to divide this number by 6 and then multiply by 6. So we get about 300 meters.